My goal today is to understand within the phase estimation thingy, what is these? Like how to come up with these. I don't fully understand yet the whole thing. I mean, so those are the main pieces, right? So you've got the inverse QFT here. Then you've got this here, which we kind of saw in the previous video. Um, that's how the factorization problem is translated, so that you can use this quantum circuit. Which, if I remember well, I'll have to recap, but it's about finding the cycles of this function. And once you find the cycles, then you can figure out what's the number, and then you do a bunch of classical operations with the GCD, the greatest common divisor, exactly. And then you kind of somehow have it's a classical processing that you have here. Then somehow you kind of you see if you got to run this again or not. I think that the whole concept here is that this is a bit of a trial and error kind of thing, where you try. Exactly. So look at this. That's what kind of thought. So it's like you pre-calculate. Okay, so you actually do something before that, which is you calculate what are those gates, because this is what you're going to do a trial with, and then you do the trial, and then if it works, and if not, you try something. You try something else. I think that's the concept. Okay, so let's just hide this, and then I think so. This is what I went through next time, and I wanted to go through these now. What is this? Why do I have this open? So, period finding in Shor's algorithm. Finally, it is time to put everything together to solve the prime factorization, the key component in hacking, blah, blah, blah. The phase estimation algorithm can be summarized in the following quantum circuit with the chain of unitary operator U. Okay. Then the inverse of the Fourier transform. So we need to find the period, and this was the whole thing, was that the problem is transformed into finding the period of this function. And this is something that it's why this is this way. It's probably out of the scope for me in this channel, but I mean, I think it was 2 videos ago. I basically, or early in I don't know if it was the last video or not, but I took a look at this. I'll definitely revisit that, because I want to make sure that I feel comfortable with this. But that's the whole point, is transform the problem into that, and then you solve it by finding the period of that modular function. We will magically define an operator U with its eigenvalue containing the period of F. So okay. So this means you define a U which has an eigenvalue that contains the period of F. But it's the period you're trying to find. So how do you do that? Phase estimation is about finding the eigenvalue of the unitary operator. Therefore, you can use Therefore, we can use it to compute the period above. Exactly. The eigenvalue of this U. Because this eigenvalue contains the period, and then if you find that eigenvalue, then you can find the period, and if you find the period, then you have it. And finally, we find ways to implement the chain of unitary operators U effectively. So unitary operator U will be defined like that. Okay. So basically, what we're trying to what this is trying to say is, so how do we implement that function? Because at the end of the day, let's just think a little bit. Let me go back here one step. Which is what is confusing to me is that the inverse of the quantum Fourier transform is supposed to give it. So if you give it if the input is, if I remember well from the QFT videos that I did, if you give it an input of like a superposition that encodes a set of frequencies, then that is going to basically expand them into the actual wave. Because that's sort of the inverse of what the Fourier transform does, which is if you encode a wave function, then it tells you the frequencies of that it's made of, right? So essentially because this is, so that's why we're putting this in here, right? So it's like we've got a superposition and we want to encode the frequency of that function, and so this is, this is done this way, which now we're trying to understand why it's done this way. So okay, so it's not that you're doing the operation, you're not calculating those things necessarily, but you're trying to encode the frequency of that. Pretty fancy. Okay. Yeah, but at the same time, it's like, this is the way it's defined. It's like, okay, so you've got y, which is our, I guess, superposition, kind of, uh, and then its eigenvalue and eigenvector of u are. Okay. So let me just take that slowly, step by step. So here we define the x times y mod n. So that's how you should define u times y. Because this y is here and here, so but then the y I assume here, this y is a, correct? Or not? Or is a what you're trying to find? Now it seems it's a because it's your input, right? So this is like you've got your input and then you apply u and then you get that. Okay, but let's see. So we're gonna skip the proof, but the idea is, okay, so basically the magic here happens. So I'll try to see if I can figure that out later without the maths, but this is basically telling you the eigenvector. Okay, so this is basically telling you that this can be, so this u can be expressed like that. Because of all, I think that's because of the way, sort of the properties of gates in these quantum circuits, right? I think we can derive this from that. Okay, in the proof we introduce the period r to simplify the expression that establishes a relationship between the eigenvalue and the period of f. R. Okay. Is this proof really heavy? Appendix to the Schroeder's algorithm. Proof. Okay. Not interested in that right now. Maybe later. So, but this, okay, so there's just some magic here in terms of how this is defined. Okay, so this is defined, and then it's just, okay, but that's not, okay, but maybe that's not what's interesting, because I want to try to understand not why this works, but like what's the implementation of u. In the proof, we introduce the period r to simplify the expression, blah, blah, blah. Period finding. This is very important. We reformulate our period finding problem into a phase estimation problem to find the period. The phase estimation problem. So we find the eigenvalue of u. Since you have r eigenvectors, the phase phi in the phase estimation equals s divided by r, where s is an integer in the range of 0 to r minus 1, and each eigenvector corresponds to a different eigenvalue. But there is one big catch here. To solve the eigenvalue, we need to know the eigenvector, but we don't know the period r, and therefore we don't know the eigenvectors. Fortunately, we don't need to. We know the superposition of all eigenvectors. Let's create a superposition with all the eigenvectors. Okay, so I kind of smell where this is going. So you want to create a superposition with all the eigenvectors. It equals 1. The concept of quantum parallelism allows us to compute the outputs of a function in parallel. So we just compute the superposition of all the inputs. If we pass it to the phase estimation, we will compute the phases of all eigenvectors in parallel. When we make measurements, each peak below represents the phase value of one eigenvector. Okay. Next, we'll find the value of r from these measurements. Probability amplitude. Next, we'll find the value of r. I'm trying to scan the whole thing first because I see that it's at least it's a bit dense for me to follow right now. There's a lot of stuff that I just have to jump over. A number can be expressed with a continued fraction representation by expanding the reciprocal iteratively. For example, 415 divided by 93 can be exactly defined as 4267. Okay. Okay. The last step in the period finding converts the measurement into period r. The measurement's approximate s divided by r with s and r as an integer. So let's use one of the peak measurements above, say 427, to compute r. Okay, so this is the peak here, 427. The first register used to estimate the phase has a range from 0 to 511. This subjects to the number of qubits we use to estimate the phase. So our measurement is 427 divided by 512, 0.83398. First register used to estimate the phase has a range from. Okay, we want to approximate it so it will fit some value of SR. We apply the continued function and check whether the corresponding answer makes sense. If not, we expand the reciprocal further until we find the answer we want. Without telling it, the continued function can be calculated with the following equations. Okay. D0, R0. The first expansion results in D0, R0. So D0, R0, this is, D is the same as S, we just have the example both coming from a different source, and R equals 1. This is not the answer we want. Period equals 1 is obviously not the non-trivial answer we want, so we will reject it. The next approximation, R1, is 1 again, and we will reject it. For the third iteration, D5 and R6. So 5 divided by 6 is 0.833333. S5 with a period of 6 makes a lot of sense to us. Let's verify a few more things before we proceed further. 5 and 6 are co-prime, no common factors. R equals 6 is even. N, x to the power of r divided by 2 mod n does not equal minus 1. After this is verified, we can proceed to the classical post-processing part that shows algorithm to compute the prime factors. Put it together. So let's put everything together. We want to find the period of f below. We have two registers. The second register should have enough bits to hold n. Correct. So those are, I guess, these registers here they're talking about, right? Correct? Correct. The first register has d qubits, which it needs enough precision. So okay, so 4 for 15. Is that the same example we got? Like 4, yeah. So the first register has d qubits, which have enough precision to estimate the phase. We can pick t as days. Okay, so you basically need an amount of qubits. We use d Hadamard gates to prepare the first register into a uniform superposition and prepare the second register to be 1. Okay, so this is what they do here, and this is what we do here. This will bring the system to whatever. The circuit above can be viewed as a nice approximation to this. 1724 313 4157. Really? We apply the inverse quantum Fourier transform to the first register. The superposition comes. Yeah, okay, but so this is skipping this right now. This, which is what I want to know. Then we use the Cottian fraction family computed period to be 6. Here's a summary of the whole flow. So this is what I'm trying to understand, because I think if I can understand that without the mathematics sort of intuitively, then I can understand the whole thing intuitively as well. Complete pre-finding algorithm, short algorithm. The remaining sections will just close up some details that we have not covered. Modular exponentiation. The last piece of the puzzle is the implementation of the chain of U gates below. We will go through the explanation relatively fast with the intention of demonstrating the major steps only. Let's make some definitions. U operator, yeah, modular multiplication, modular squaring. Okay, so it's defining, okay, x, y, so x times this, modular squaring. Now we can use the modular multiplication and the modular squaring above to build the modular exponentiation below. We start with some ancilla beats and the eigenvector u. We apply the u operator Then we apply the modular squaring repetitively. Oh, cool, some actual examples. Now we can use the modular multiplication and the modular squaring above to build the modular exponentiation below. So second register. So what is it doing here? Yeah. U to the power of 2 to the power of 1 to the power of 2. It's like u to the power of 2 to the power of 2. We start with some ancillary bits 1 and the eigenvector u. We apply the u operator. We want to turn 1 into x. But what the hell is x? What the hell is x? Then we apply the modular squaring repetitively. To perform that. Okay. Finally, we apply the modular multiplication. The output is what we want. This times this. So I assume that's what we're doing. So here's the final circuit using those modules in producing the modular multiplication. The second half of the circuit simply reverses the operation to recover the ancillary qubits. So you've got u. You've got the ancillary qubits. And then basically, this is step 1. Then this is the thing that you do like many times, and then you do like a multiplication, which at the end of the day, what it does is probably gives us here, the answer that we want. And then that's what we that's what we covered in other videos as well. That's basically because there's probably going to be some entangle happening, so you want to disentangle stuff here. You want to disentangle the ancillary qubits with your actual result. Here are the circuit for some of the model implementations. Okay. Crazy. This is a circuit for factoring. This is the circuit for factorizing 15 with x equals 11. Okay, so what is this coming from, people? The circuit described needs 12 qubits. To fit into a 5 qubit machine, it is further optimized. Okay. I mean, the optimization is like, I guess we don't care about this right now, about the optimization. But I can't remember where the x is coming from. I can factorizing 15 with x11 because I think this has to do with let me just go back to where can I find the whole thing. I think if I go to his quantum computing series or this here, I think no let me see. Sure. Okay, quantum gates, quantum algorithm, Shor's algorithm, phase estimation. I think it's either this one or this one. I think it's this one, probably the first one, where they explain the RSA algorithm. And then, okay, so here's the example of, it's the example of 15 as well. Because this is exactly what those examples are doing. Complexity, prime factorization. So here's an example of So we need to formalize the solution in the usual way. Let's find the prime factors don't have the equation below. Magically, these equations end with the number 7 and 3, which is our answer. But it's not a simple trick. So there's many mathematical theories behind them. Basically, it's to find a number 8 in our case with it. So you've got to find that 8. And maybe that's the x, right? With its square equal to the term on the right below. So let's try our luck again. Start with random guess x2. Yeah, I'm assuming that's what's okay. So I'm assuming that's what's, because this is then the whole idea, right? So you pick an x, you start with random guess, you pick an x. We want to know whether x and n are co-prime, and then so 3 is the common factor. But I don't expect to have a frequently in real problems. X is a co-prime with n. Now we compute the following series of power functions. This function has a period of 6. The function values repeats itself every 6 values. If r is divided by 2, blah blah blah. Okay, and so we start with a guess. So we start with a guess on x and verify whether it is co-prime with n. If not, we use GCD to find the prime factors. Otherwise, we compute the period of the power function. If the period is even, the number we're seeking is this. The one underlying the red below. If r is not even, we take another guess on x and try again. So this is the whole. This is what I'm kind of like. This is how the whole thing is wrapped up. So it's like you kind of give you kind of try. Okay. So in practice, you have a pretty even chance of getting the period to be even. Okay, so that's pretty nuts, though. I mean, it's just okay. So you're just trying. It's pretty nuts. I mean, you're giving you choose an x and then you follow that. So you try if the period you find is even. Because if your period you find is even, then you kind of you have a recipe to know what's then the number you're looking for, and then you can do the whole thing with finding the prime numbers. The one, so if it's not even, then we take another guess on x. Still don't really know why. We have a pretty even chance of getting a period. So many choices of x will lead us to the right solution. The odds are pretty favorable. Okay, so it's like there's no just one solution. Many of them. Okay, so let's find the period of the model function. Bounded area. No. Okay, let's see for the worst case scenario. Okay. Okay, so this is okay. So this is the x. This is kind of what you're guessing, right? So with x11, and you're trying to factorize 15, and you've got x11. The circuit described required needs 12 qubits, 55 qubit machine. No, okay, that's fine. So we ignore the optimizations. Why are they so small? Why are they so small? 7 times 1 modulo of 15, sometimes 7 modulo of 15, sometimes 4 modulo of 15, sometimes 13 modulo of 15. Just so without explaining them, here are the circuits for some of the module implementations. Pretty heavy. And it's complicated. That's complicated. I'm trying to think what is a good next step to try to follow that, because basically, why are they measuring that? Why are there some measurements here? That doesn't make much sense. But is it then that it's all this EU gate is all about control nodes, or? So you first want to apply these in a way that it gives you this, right? That's what the whole thing is saying here, ux. Then you apply j times the one that makes the exponential part. But why? Okay, modular. So the modular squaring. So modular squaring. Okay. So you're kind of squaring this. It's the modular multiplication and the modular squaring both to build a modular exponentiation. And then modular multiplication is x times this, which is this here. So this here. Start with sensitivity 1 and the eigenvector u. But what is the eigenvector u coming from? You should see my face right now. We apply the u operator. So you get x. So you get, okay. So you get x times u. Then we apply the modular squaring repetitively. It still doesn't tell me how, it's outlining the steps, but it doesn't tell me what's the... Finally, we apply the modular multiplication. X times u. So then we turn x times u into this. Then we perform it again, then we perform it again, then we perform it again. And that's kind of the general, okay, but I don't know what j is, but okay, so that's what you go for. And then when you have that, you apply multiplication. Which basically turns that second part into x times 1. Okay, so then you apply this multiplication, which basically turns that u into this. Sure, but that's not telling me why or how. Like, that's just outlining the steps. That's just outlining the steps. Example. This is a circuit for factorizing 15 with x equals 11. Right. Definitive 5K machine, so. 11. Well, yeah, but. So this seems like it's 7 times 1. This is... No. What is this? No, that's not correct. What is all this? What is all this? Because these circuits basically... they're all the same. These, and these. I think I'm gonna need. I think I'm gonna need to find another. I think I'm. I definitely have some big gaps, but I understand the basic structure of the whole concept. But I have some big question marks still, and I think I'm gonna have to find. I'm gonna try to find another guide to complement my perspective on that. I think. So let me just recap here in general, of where I am mentally, um, because this is a good guide, but I feel it just jumps too much. So this definitely go through that. I think it's super. That's helped me a lot to build intuition up to a certain level, but I'm kind of missing like that little detail yet inside. So just a quick recap. So basically, the whole thing here is, first you need to understand that Shor's algorithm, sort of in general, is based on rephrasing the problem of the prime, of finding the prime factors, to basically finding the period of this function here. And in order to find the period of this function here, what we're doing is we're basically so we're basically trying to encode. So we're picking a number x, and then we're trying to find the period. I'm having trouble myself with that. So prime factorization. So you're picking an x, exactly, and then you're trying to find the period. And if that period fulfills certain characteristics, then you're done. If it doesn't, then you're going to try another x. That's kind of the whole, how this is classically wrapped. Now, the QFT is an important part of it because it helps us find the period. The inverse is what matters, right? The inverse. I mean, I covered the QFT in another video series, so you can go check that out as well. But it's still like I'm having big trouble here. I'm having big trouble with phase estimation. So the idea is that, based on, I want to find sort of I think it was here. There's like an overview of the whole circuit, the quantum part of the circuit. Down here, exactly. So the point here is that this part down below, I mean, this whole thing here is something that it depends on the x that you choose, that you're trying, right? It depends on the way you build, because the idea is you build a circuit like during your classical computations. You kind of build a circuit, and then you just send it to the QPU in that sense, and see what results you get out of that. So that's something you kind of pre-calculate. What are you going to do in here? And this is kind of what I'm having trouble understanding. Because basically, period finding. Dun, 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 dun. So, but is this here the result of the inverse quantum? Inverse. I think that's going to be the easiest next step for me, is to try to go through another guide, kind of starting from scratch, and see if that helps me fill in the gaps. See if that helps me fill in the gaps. Shor's algorithm. Shor's algorithm. We could even maybe try to watch actually a video. Prime numbers. So maybe phase estimation. Phase estimation. Phase estimation algorithm. Did I check David's blog, because he usually has good stuff in it. Apply controlled unitary gates. Yeah, maybe I'll try to. Maybe I'll try to go through that. Maybe I'll try to go through that next time. Seems so. Is this a quantum subroutine that allows us to estimate eigenvalue given its corresponding eigenvector in a unitary matrix? It's a building block of many quantum algorithms. It shows algorithm, quantum algorithm for linear systems, equations. Sorry, to Monte Carlo. It's possible to present the theory behind phase estimation and teach you how to implement classical simulation of the algorithm in Python. Estimate the eigenvalue given its corresponding eigenvector. In the unitary matrix. I got to figure out another way to do that. I feel I'm far. I think there's sort of a huge gap ahead of me to kind of grasp that concept intuitively. Got to sleep on it, and yeah, good. But I feel I'm moving a little bit forward, a little bit forward at least. It's definitely, yeah. Cool, perfect. Stay tuned for more.